Welcome to the second part of the series on the birthday paradox. In this part, we're going to study the problem where there are m days in a year and there are n people in the room, a more general version. And we wish to know what is the probability two people in the room have the same birthday. Just like the previous video, we're going to use the same notation. The event AN represents the event where all n people in the room have a different birthday, and probability of A of n is the probability of A of n being true. A black circle or dot represents a person in the room. A blue circle represents a day that no one in the room has a birthday on, and a red circle means someone in the room has a birthday on that day. Now, first suppose we have an empty room and person 1 walks in. There are m blue days in this case because all days are available. And we want to know what is the probability that person 1 has a different birthday. Just like the last video, the probability is 1 since there's only one person in the room, and that implies that everyone in the room has a different birthday. Now suppose person 1 is born on day 1. Let us represent an edge between the two, between person 1 and day 1 to signify person 1 was born on day 1. And we're going to mark day 1 in red, meaning that day 1 is taken, or someone, in this case person 1, was born on day 1. Now suppose person 2 walks into the room. We're going to use the same principle we used in the previous video. In order for everyone in the room to have a different birthday, all the people who entered the room before them need to have different birthdays, and the person entering needs to have a different birthday from everyone else already in the room. When person 2 enters, there are m-1 blue days and 1 red day. We want to know what is the probability that all 2 people, or in this case everyone, has a different birthday. Using the principle we stated, that would be the probability that person 1 has a different birthday times the probability that person 2 was born on a blue day, or person 2 was born on a day different from that's not on a red day, or the day that someone else was born in. We computed in the previous slide that the probability that person 1 has a different birthday is 1, and the probability that person 2 is born on a blue day is m-1 divided by m, because there are m-1 blue days and people are born uniformly at random. Now suppose a third person walks into the room. For everyone to have the same birthday, using the principle we defined, both person 1 and 2 need to have different birthdays, and person 3 needs to be born on a blue day. From a previous slide, we know that the probability 2 people have a different birthday is m-1 divided by m, and the probability that person 3 was born on a blue day is m-1 divided by m, since there are m-2 blue days. And let's suppose person 3 was born on day 3. Now suppose a fourth person walks into the room. The probability that everyone has a different birthday using these principles is if 3 people, person 1, person 2, and person 3 have different birthdays, and person 4 is born on a day that neither of them are born, or person 4 was born on a blue day. Now we can write the probability that 3 people have a different birthday as probability of A3, since people arrive uniformly and independently at random. And the probability that person 4 was born on a blue day is m-3 divided by m. Now, we've computed it for days up to 4 people. And what we want to do next is we want to generalize this for any n people. Now, suppose there are n-1 people in the room with different birthdays, then there are going to be m-n-1 blue days and n-1 red days. And using the principle we defined before, the probability that all n people have a different birthday is the probability that the n-1 people who entered before the nth person has a different birthday, and person n was born on a blue day. Now we can simply write the probability that n minus 1 people have a different birthday as probability of a n minus 1. And we're doing this because we can do this because people are born uniformly and independently at random. And we can also write the probability of person n being born on a blue day as m minus n minus 1 divided by m, because there are m minus n minus 1 blue days and people are born uniformly at random. Now, this is nice because we have a recursive formula. We are writing our recursive formula like this. Now, we can write probability of a n minus 1 as the probability of a n minus 2 times m minus n minus 2 divided by m. And once we sub this formula right here, we get this expression. And now we can continue to do the same with this one. We expand this expression and we plug it in and we get a bigger expression. And we keep doing that all the way until we hit the and this number is reducing. It's n minus 1, n minus 2, n minus 3, and we keep repeating this process until we arrive at probability of a2 times a bigger expression. Now, we computed the probability of 2 people being in the room and having different birthdays. You can go back and look at it, but I'll save you the time. It's m minus 1 divided by m. And what we have here is m minus 1 divided by m times m minus 2 divided by m times m minus 3 divided by m. In fact, we can write this in a nice expression. We can write it as this one right here. We can write this as the product of that goes from I to n minus 1 of m minus I divided by m, which is the product, and we can divide this by m by m minus I divided by m by m becomes 1, and we have I divided by m here. Now we're going to use an identity which we will see over and over again, and that identity is 1 minus x is approximately e to the negative x. I see this identity being used a lot when it comes to analysis of this sort. And in this case, we're going to use, suppose x equals I divided by m. 1 minus I divided by m is approximately e to the negative I divided by m. And we're going to plug it in using the same identity. Using this identity, we would get this expression right here. We can use the, since this is a product and since we have exponentials here, we can use the property of exponentials to add up the exponents right here. When we add up the exponents, we get e to the negative summation that goes from I to n minus 1. And we can also use another identity, which is the sum from I equals 1 to n minus 1, or the sum of the first n minus 1 numbers to be n times n minus 1 divided by 2. And we can take m out, and a summation of this would simplify this expression to e to the negative n times n minus 1 divided by 2m. Now we can simplify this even more and simply just write it as e to the negative n squared divided by 2n. This is the final approximation we have when there are n people and m days. We have shown this one, finally. Now the birthday paradox isn't a toy problem or a party trick. It has real-world applications. In the next video, we will focus on the applications of the birthday paradox, specifically in cryptography. Now if you like this video, hit subscribe. Also feel free to comment about your questions and thoughts about this video. Also please comment about what you'd like to hear in future videos. Thank you.